Today, we will study Ceva's theorem. If three Cevians Ax, By, Cz, one through each vertex of a triangle ABC are concurrent, then Bx upon Xc into Cy upon Ya into Az upon Zb is equal to 1. This is known as Ceva's theorem. Here we will study some of the terminologies which we will use frequently in geometry and in this theorem also. So the first one is Cevian. Cevian. So Cevian is defined as a line segment from the vertex to the given point on its opposite side. Any given point on its opposite side is known as a Cevian. So x is say any point on line BC, then AX is called as a Cevian. So Cevian is a general form of a line segment joining the vertex to any point, other point on its opposite side. We already know some of the Cevians, such as the altitude, a median, and a angle bisector, which we are using frequently, but we were never naming it as a, it is a special case of a Cevian, and it is altitude. So this terminology Cevian is came from the Italian mathematician Giovanni Ceva, who has published in 1678 this beautiful theorem is known as a Ceva's theorem. And so if three Cevians x, by, cz, one through each vertex of a triangle ABC are concurrent, then bx upon xc into cy upon ya into az upon zb is equal to 1. So the next terminology is concurrent. What is concurrent? We know that if there are any two lines, they will either intersect or will not intersect. The two lines which are not intersecting each other are parallel lines. So that is a property of a parallel line in Euclidean geometry. So if there is no intersection between two points, between two lines, then it is a uh, these lines we can call it as a parallel lines. So if there are two lines, then they will intersect in a point. So their point of this point is called as the point of intersection. Now, suppose if there is a third line which are intersecting these two lines, so then it may be possible the line is intersecting like this or like this, or it may be possible that line will pass through the intersection of these two uh, lines which is already intersecting, or and then we can say that the three lines are passing through the same point, and that is called as a point of concurrency, and the lines are said to be they are concurrent. So if more than two lines are intersecting through a point, then they are called as a concurrent lines, and the lines are said to be concurrent lines. The third one is a collinear terminology. So that is collinear. Collinear. So collinear means it is regarding the points. When there are 2 points, we know that a line is passing through the given any 2 points, or we need 2 points to draw a line. But if there are, suppose there are some other point, say like this is the third point, say, So this may be possible that this point may lie on this line or may not lie on this line. So on this side, say, or on this side, or exactly on the line. So if the 3 points are lying on the same line, on the same line, then the points are said to be collinear points. So the lines are concurrent and points are collinear. We can say that if more than two lines are intersecting in only one point, or their point of intersection is common, then they are concurrent. And if more than 2 points lying on the same line, then the points are collinear. So we can make a statement: the lines are concurrent and points are collinear. We have the points x, y, and z on the sides BC, CA, and AB respectively. We have three Cevians: AX, BY, CZ, and these three Cevians are concurrent at point P. Now we have this length BX and XC, then CY and YA, AZ and ZB. So the ratio of BX upon XC into CY upon YA into AZ upon ZB is equal to 1. So we need to prove this result. So this is the condition that the three Cevians AX, BY, CZ are concurrent if and only if they are satisfying this condition, that is Bx upon Xc into Cy upon Ya into Az upon Zp is equal to 1. The area of any triangle is equal to 1 half base into height. Suppose I have this triangle ABX. Then what I will do, I will take Bx as the base, and then the perpendicular from A to line Bx will be my height. The area of this triangle is defined as 1 half Bx into the height. So if I draw, say, this height, so this is a height, say h is the height. So the area of this triangle ABX will be 1 half base into height, and say this height is h. Area of triangle ABX is equal to 1 half Bx into h. Similarly, the area of triangle ACX is equal to 1 half Cx into h, because this height is same for the both the triangles ABX and ACX. Therefore, dividing 1 by 2, we get Bx upon Xc is equal to area ABX divided by area ACX. So this is the result because the heights are same for both the triangles ABX and ACX. Now if we observe, this point A is common to both the triangles, that is ABX and ACX. Therefore, and the point X as it is lying on line BC, therefore the perpendicular from A to BC will be same for both the triangles, that is ABX and ACX. So making use of the same thing, we can also say that if I draw the perpendicular from point, let us say this is H dash, okay, then area of triangle BPX will be 1 half BX into H dash, and area of triangle CPX is equal to 1 half CX into H dash. So this means by making the same thing, that is area BPX is equal to 1 half Bx into H dash, area CPX is equal to 1 half area CPX is equal to XC into H dash. Bx upon Xc is equal to area BPX divided by area CPX. So this is because areas of a triangle having same altitude are proportional to their bases. So this result, so these Bx and Xc are the base of the respective triangles and having same altitude. Therefore, Bx upon Xc is equal to area ABX upon ACX is equal to area BPX upon area CPX. Bx upon Xc is equal to area ABX divided by area ACX is equal to area BPX divided by area CPX. So now we come to know that the areas of a triangle having same height are proportional to their bases. Now we know that from the ratio, if we know that A upon B is equal to C upon D is equal to some constant, say K, then this implies A upon B is equal to C upon D is equal to A minus C upon B minus D. So it will bear the same ratio, that is K. We will make use of this uh, result from the ratio, and we can say that Bx upon Xc is equal to AB area ABX upon area ACX is equal to area BPX upon area CPX is equal to area ABX minus area BPX divided by area ACX minus area CPX. So that is equal to this area ABX minus area BPX will give area APB. Similarly, area ACX minus area CPX is equal to area APC. Area ABX minus this area, so that is area ABP. Similarly, area APC for area ACX minus area CPX, this area. So we'll get this area, that is area APC. So this means we are getting Bx upon Xc is equal to this triangle, area of this triangle. Similarly, this triangle. So we can say that excluding this area for Bx and for say excluding this for Cx. So Bx upon xc is equal to area APB divided by area APC. Similarly, Cy upon Ya is equal to area BEC divided by area APC. Similarly, Cy upon Ya is equal to area BCP divided by AEB, and AZ upon ZB is equal to area APC divided by area BCP. Therefore, Bx upon Xc into Cy upon Ya into Az upon Zb is equal to area APB divided by area APC into area BCP divided by area APB into area APC divided by area BCP. So this BCP and this BCP will get cancelled. This APB will get cancelled. This APC and this APC will get cancelled, and it is equal to 1. And hence, the product of the ratios Bx upon Xc into Cy upon Ya into Az upon Zb is equal to 1. This is known as Ceva's theorem. So this condition must be satisfied by the three Cevians to be concurrent. Otherwise, they will not be concurrent. So once again, we go through the theorem. The theorem states that if X, By, Cz are three Cevians and if Bx upon Xc into Cy upon Ya into Az upon Zb is equal to 1, then they are concurrent.